Welcome to Lecture 3 of ECE 141. In this lecture, we will be talking about the signal space, right? Particularly, how do we analyze signals or represent signals differently. And actually, we can represent them with in a much easier form since the signal space is what we call a vector space. Right? So for this lecture, the outline is that we'll be discussing the baseband to the passband conversion, your complex baseband representation, and we'll connect that to what we call the signal space. So before that, let's review Fourier transform. So if x of t is a deterministic signal, so it's not random, so we know how it flows or we know the pattern, then its Fourier transform is defined by the integral equation right here. So you've already seen this a lot of times, triple E 107, triple E 35, you get the point. So just note here that j is your imaginary number. So x of f is now a complex function of frequency. This is your Fourier spectrum, the magnitude of which is called the magnitude spectrum. The phase is the phase spectrum, and I know you know that. The inverse Fourier transform is called the synthesis equation. Okay, so this is the synthesis equation. Okay? This is called the analysis equation. Okay? So basically, we're gonna analyze x of t and break it down to its frequency components. From here, from its frequency components that are known, we're gonna synthesize x of t. Okay, so note the difference of that. Some properties of the Fourier transform include linearity. If you have two signals scaled and added together, their corresponding Fourier transform would be scaled and added to create the Fourier transform of the added signals. Time dilation, time dilation property is that if we compress time, inside our deterministic function, its Fourier transform would be wider. Right? So if you have a rectangular pulse which had a sinc function as a Fourier transform, then a smaller rectangular pulse would have a wider Fourier transform. So that's what it means by dilation. Conjugation has this property. If we take the conjugate of our signal, so it's generally a complex signal, then we have this value of its Fourier transform. Basically, it will be flipped and conjugated. And next is we have the duality. If we have x of t with the Fourier transform x of f, then if we have x of t, which has the pattern of x of f, but it's in the time domain, then its Fourier transform is equal to a reflected version of your original function. Time shifting property creates this term multiplied with the Fourier transform. This is actually a phase shift. Okay? So this term here is a phase shift that depends on T0 and the current frequency at that point from the spectrum. Frequency shift is that if we have a complex number multiplied, complex number with time, or a complex carrier, as we call it. So it's a complex carrier. Right? Multiplied with the original signal, then your frequency will just be shifted by some value f sub c, which is the frequency of this complex carrier right there. An area under the curve is, if we take the area under the curve of your time domain signal, it's equal to the DC value, as we call it. If we get the value of the curve at the value of the signal at time t is equal to 0, then we're getting the area of the Fourier transform under the curve. Right? So differentiation in the time domain creates this equation. So you multiply j2 pi f with x of f. This is equivalent to your high-pass filtering. Okay? So high-pass filtering is you amplify high-frequency signals and you reject low-frequency signals. As you can see here, if f is 0, then the Fourier transform is 0. If it's high frequency, then the value is very high. Integration in the time domain creates this expression right here. You have a factor of 1 over j2 pi f. And this is actually equivalent to your low-pass filtering. Okay? So any low frequency will be amplified, any high frequency will be attenuated. If f is 0, this booms to infinity. If f is infinity, then this becomes closer to 0. And the next parts are important for our communication systems. The modulation theorem is that when we multiply x1 of t, oh sorry, this is actually the convolution theorem. Okay, so I switched them. Okay, so I switched them. So this is the modulation theorem, is if you multiply x1 of t and x2 of t, then you convolve in the frequency domain. And by duality, if you multiply in the frequency domain, then you convolve in the time domain. Okay. Modulation theorem is that, wait. Oh yeah, it's correct actually. This is the modulation theorem. If you multiply in the time domain, you get convolution in the frequency domain. Okay. Your convolution in the time domain is you multiply in the frequency domain. Right? So they're just a dual of each other. I apologize for that. The correlation theorem is that if we get the autocorrelation of, the correlation, cross-correlation of two signals, x1 of t and x2 of t, their frequency domains will just multiply, but the other one, we get the conjugate. Okay. So it follows that if we get the autocorrelation between x1 of t with itself, then we're just getting the integral of x1 of t with its conjugate multiplied to t minus tau d tau. Okay? And this actually becomes, okay, x1 of f multiplied by the conjugate of x1 of f, which is equal to the magnitude of x of f squared. Okay? So this is basically your cross correlation. And this is your power spectral density for your deterministic signal. Right. Finally, we have Rayleigh's energy theorem. What this means is that if we take the magnitude squared of your signal and get the area of that under the curve, this is your energy. This is the definition of energy. Excuse me. Then this energy can also be found in the Fourier transform. If we take the area of the power spectral density squared, right? So basically the power spectral density, no, not power spectral density. If we take the area of the power spectral density, we also get the energy of the corresponding signal. Alright. So now we know the different properties of Fourier transform. How do we apply them to our communication signals? So communication can be split into a baseband and a passband type. A baseband communication is actually the communication that is done centered at the zero frequency right here. Once it is split and moved to higher frequencies, right? So let's do that again. Once it is split and moved into higher frequencies, then we now have what we call a passband signal. Okay? So we are going to assume that these are real signals because you cannot actually create a complex signal in real life. So the real signals are what we can only observe. And real signals have what we call a Hermitian symmetry. Oops. Oh wait. Sorry about that. Okay, there you go. So real signals have Hermitian symmetry. That means their magnitude spectrum is symmetric, as you can see here. This is actually the magnitude of x of f. Okay. And whether it's baseband or it's passband, it always has an even symmetry in its magnitude spectrum. Its phase spectrum has odd symmetry. Okay? From our passband signal, consider a real narrowband passband signal y of t that is centered at a frequency f sub c. We can create its complex baseband. We can represent it as its complex baseband using the fact that y of t has a cosine component and a sine component. So we can actually break down y of t with its cosine and its sine component. Okay? We call this cosine component the in-phase component, the sine component as the quadrature component. Equivalently, if we already know yi and yq, so basically you just get the cosine and the sine component, then we create a complex baseband signal using yi and yq. So yi is the in-phase component, yq is the quadrature component. The complex baseband equivalent is this equation right here. To convert it back to the passband, you just get the real part of your complex multiplied by your carrier. Okay, so this square root of 2 here, we will see why it is there later. Okay. How do we separate the signals from a given y of t? So consider a given y of t and some in-phase yi, quadrature yq. We try to evaluate this integral right here. So you multiply y of t, which is we know is in this form, by square root of 2 cosine 2 pi f ct. So the expression inside the integral becomes this equation right here at the bottom. So we have a cosine squared and a cosine times sine term. Using your trigonometric identities, so note that we still have a square root of 2 here. We have a square root of 2 here also for both terms. That's why we have a term here that is 2, a term here that is 2. And then, if we use trigonometric identities, your cosine squared becomes 1 plus cosine. And you have double the frequency. Here, you have double the frequency, but it's a sine component. So these are two high-frequency signals and a baseband signal. The resulting integral from here, what are we doing again if we're getting the integral of a signal? Recall that it's actually equivalent to low-pass signaling, low-pass filtering or averaging. Therefore, any high-frequency signal would be lost. This will become 0, this will become 0. We're gonna be left with yi of t. Okay? So now consider that if we multiply it by sine 2 pi f ct, you can do this by yourself. You'll get yq of t. Okay? So I'll demonstrate this to you once we meet in class. Okay? It's also going to be uploaded as a resource material. So knock yourselves off. Alright. Some example. Find the complex baseband equivalent of the following signals. So you can do this by yourself by pausing this video and then doing it yourself. The answers will be discussed in the succeeding slides. Alright. So for example, the first one, the answer is straightforward. It's equal to 3. How? This 3 is the factor of your square root of 2 cosine 2 pi f ct. That's basically yi. Yq is 0 since there is no sine term. For the 2, let's expand the cosine identity first. It has a 45-degree phase shift, and you'll actually reveal a sine 2 pi FCT term. Okay? So it follows that the factor of this is 1, the factor of this is 1, y baseband is 1 plus J1. Okay? Same procedure can be done to number 3, and you'll get this answer right here. Okay? So I won't expand that anymore. You can try it by yourself. The block diagram is this. So this is what you will see in your in the resource material, that simulation file. Okay. And the low pass filter represents averaging. So by using the low pass filter, we'll get the the in phase and the quadrature components. And these are already in baseband. And in computers, using computers, digital communication, we use computers, etc., etc. They can be represented as complex numbers. Right? And what are complex numbers? Recall that complex numbers can be plotted in a complex plane. Right? And those are vectors. Right, so let's review vectors. So from a mathematical perspective, a vector is a quantity with magnitude and direction. You already know this. For example, if a ball moves 2 units to the left and 3 units to the forward, or 3 units upwards, whatever, we get this vector expression in the middle right here. So it can be represented in different ways and can be plotted on a Cartesian plane. But it can also be a complex number. So in this case, we have a vector in 2 dimensions, dimension x and dimension y. In general, vectors can have n dimensions. So basically, the vector space, right? So this, I'll introduce to you the vector space. A vector v can be generally represented by an n by 1 column vector, where n is the number of components, or the number of dimensions. So the vector space is formed when a set of functions called a basis, this should be a set of vectors. Set of vectors called a basis, okay, is linearly combined. What do we mean by linearly combined? We combine them using weights, scalar multiples. Okay? So for a vector with n components, the basis has at least n elements. For example, this vector right here can be represented by this times this vector, this scalar times this vector, and so on and so forth until you have this expression right there. And this is a linear combination that represents your vector v. So the scalar values v1 are weights and can be complex valued. So this is a vector space. And what's unique about a vector space is that it has what we call the inner product. The inner product is a special operation, can be defined for vector spaces only. So if you have two vectors v1 and v2, the dot product or the inner product between them is defined by this to this, which is basically you just multiply the elements. Okay? You multiply the elements, corresponding elements, with your second vector conjugated. Okay? Or basically you just have a column vectors multiplied to each other. The column vector of 2 will be transposed using the Hermitian operator. That means it will be transposed and then conjugated, multiplied by your column vector v1. It follows that if we flip the operations, right, flip the operands rather, the operation will have a conjugate value right here. So what is the use of inner product? If we have your vector v1 and we get its inner product with a basis, in this case a sub x, we're projecting v1 on that basis, and we actually get a component of your vector. Okay, the same here. So this is the y component, this is the x component for your two-dimensional space. And same is true with a vector v2 right here. Right. What is the physical interpretation of an inner product? Well, projection is 1. If you take the norm of the vector, which is also called the length of a vector, we're just getting the square root of its inner product with itself. And a property of inner product or norm is that if we have the sum of two vectors and we take the norm of that, it's less than or equal to the sum of their norms. So this is called the triangle inequality. How? So if we have two vectors right here, if we add these two vectors, v1 and v2, create a third vector, which is their resultant or sum. Right? Since this is a triangle, then this length is related to this length by an inequality. Okay? Cauchy-Schwarz inequality is a property of inner product. If you take the absolute value of an inner product, again, an inner product, the result of an inner product is a scalar. Your Cauchy-Schwarz inequality, this should be less than or equal to v1, the norm of v1 times the norm of v2. Okay? So this is your Cauchy-Schwarz inequality. Right. So some vectors in our vector space can be orthogonal and orthonormal. Orthogonal means these vectors have a zero inner product. Right? So that means if we get their axes, okay, that means their axes have a 90-degree difference. So this is an orthogonal vector. Orthonormal, if we get the dot product of the vector with itself, it will result into 1. So that means the length of these vectors is equal to 1. So it's normal. Okay? Two vectors that satisfy orthogonal and normal means it's an orthonormal vector. Right? And for an n-dimensional vector space, we can create an orthonormal basis for that vector space. For example, we've already seen this from this example right here. This, getting the dot product of this with itself, it's 1. Getting the dot product of this with itself is 1, etc., until here. If we get the dot product between these two, we get 0. This is an orthonormal basis for an n-dimensional vector space. Right? So what's the use of all this? Why do I need to know this information? Well, actually, signals are vectors. Okay? We can represent signals as complex numbers. That means we can also represent signals as vectors. So our scalar multiples are multiplied to some form of unit vectors. In this case, for our passband signal, it's actually, there are two signals. Its components has two signals, the cosine component and the sine component. These are actually some form of your unit vectors. So if it's a vector space, our signals, it should have what we call an inner product. Let's define the inner product. So the inner product between two signals is defined as the integral, okay, of their product. The integral of their product. So let's see how that definition holds. If we take the inner product of the unit vectors with themselves, they should be 1. If we take the inner product of the two unit vectors between them, if we're gonna take the product of the unit vector between the unit vectors, it should be 0. So that makes cosine and sine orthonormal. And we want that, right? So consider the inner product between them. You get this expression right here, right? And if you take the dot product of that, the inner product, if we get, excuse me, if we evaluate this integral, you actually get 0. Makes them orthogonal, right? If you take the, excuse me, the inner product of the signal with themselves, so here and here, we actually get 1. That means these two signals, cosine and sine, form an orthonormal basis for our signals. So that means it's a two-dimensional space. So is it possible to create an n-dimensional space? So yeah, it's cool and all, we have a two-dimensional space, that's cool. Can we create an n-dimensional space? Let's look at the Fourier series. For any periodic signal, we can represent them as a series of sinusoids, complex carriers, as you can see right here, which is actually the same with the definition of a vector space. This C sub k is a complex number which corresponds to the weight of a basis. Okay? So loosely comparing both terms, well, it follows that this signal e to the j2 pi k f naught t for varying values of k forms an orthonormal basis for this signal vector space. So it's up to you to prove that the basis is orthonormal. Okay? So generally, we can actually define an n-dimensional vector space for signals. We call this the signal space. So this signal space will be an important concept to you when we're going to talk about digital communication systems. So let's generalize it. We have a set of basis functions phi sub k of t. If our signal can be represented as such weighted sum of different signals phi sub k from k equals 1 to n. So again, we call this your synthesis function. So similar to your Fourier series. Then this signal right here can be represented as a vector with this representation. Okay? For your Fourier series, your basis is your carrier. Right? What are the if we redefine the signals as such, what are the other interesting things that we can get? Signal energy. Recall that the energy of the signal is equal to your magnitude squared of the signal, and you get the integral of that. What if we get the inner product between the signal with itself? Here and here. If we get that, then we also get the energy. Recall that this absolute value of x of t squared is can be rewritten as x times x conjugate. So this is an interesting concept actually. So by getting the inner product of a signal with itself, you can actually get the energy of the signal. For example, let y1 be this signal, y2 be this signal. Compute their inner product. If you get the inner product, so let's do the vector space approach. Then we can represent them as vectors. Okay? And then we multiply or get the inner product, we get 3. If you try to use the integral approach, you have this solution right here. Right? But the result will just be the same. Right? So the key point here, the high frequency components will become 0 after the integral. Right. So finally, we have the concept of the Euclidean distance. Being a vector space, it follows that the signals can be represented on an n-dimensional plane or space. Okay? And that means between two signals, there is a form of distance. Okay? If we take the distance between two signals, we're just getting the norm of their difference, right? And actually, you can think of this as the likeliness. Oops. Okay, so try to. Oh, come on. Sorry about that. So this is the likeliness between two signals. If the distance between them, between two signals, is 0, that means they are the same signal. Okay? So this is an important concept when we're going to deal with what we call digital symbols. And more about that in the next lecture. So this is the end of this lecture. I hope you learned a lot. If you have any questions or clarifications, do not hesitate to leave a comment in the comment section below. Thank you very much. I'll see you next meeting.